We were looking at the Miller-Rabin test in the previous class. So, the steps in Miller-Rabin are as follows. If the so we will assume that the input is an odd number and not a prime power. We choose a random A and compute A raised to R, A raised to 2R, A raised to 4R and so on up to A raised to 2 to the SR. Now, 2 to the SR is equal to n minus 1. If after all these computations, if we find that A raised to n minus 1 or A raised to 2 to the S times R is not equal to 1, in that case we declare as composite. And in between, if in any of the steps we find a non-trivial square root of unity, then also we declare that the number is composite. These are genuine conditions under which we can declare the number as composite, because for a prime number, A raised to n minus 1 must be equal to 1, and a prime number must not have any non-trivial square root of unity. Non-trivial square root of unity means we found some number such that A raised to 2 to the I times R is equal to, let us say, alpha, where alpha is not equal to plus or minus 1, but A raised to 2 to the I times 2 or I plus 1 times R. So, A raised to 2 to the I plus 1 times R is equal to 1. This would mean that alpha is a non-trivial square root of unity. Now, we have argued in the last class that primes, if you take n to be a prime number, then there will not be any non-trivial square root of unity. That is, there cannot be any numbers other than 1 and p minus 1, which squared gives us identity. Here, this number A raised to 2 times I to A raised to 2 to the I times R, that turns out to be a number which is not plus 1 or minus 1 or p minus 1, but squared it gives us 1. Okay. So, these are both genuine conditions under which we will declare the number as composite, and if these conditions are not met, then we had declared it as prime. What we need to argue is that on every composite number, this algorithm correctly declares it as composite with more than 50% chance. It is clear that this algorithm will say the correct answer for every prime number, because a prime number will not be declared composite ever by this algorithm. So, the only error that this algorithm can make is declare a composite number as a prime number. We will show that that happens with less than 50% chance. Okay, so, in the algorithm we chose the A from the set 2 to n minus 1. Okay. Now, let us look at this question. If n was a composite number, then how many of these A's will pass these tests? So, if we call this as test 1 and this is test 2, how many of these A's will pass the test? So, the A's which pass this test essentially bears a false testimony to the primeness of n. So, n was actually not prime, but just because the A that we chose passed these tests, we would incorrectly declare the number n as prime. So, we want to count the number of false witnesses, and we want to say that they form a very small set. So, that would also mean that the other elements which would correctly testify that the numbers are composite, they are large collection. We will show that at least 50% of the numbers will correctly identify the number to be composite. In order to show that, what we will essentially show is that these numbers which bear false testimony to the primeness of n will be a subgroup of a certain group. It will be a proper subgroup of a certain group. So, if you look at the group Zn star, okay, so this is the set of all elements such that GCD Xn is equal to 1. Okay, we will assume that x lies between 0 to 1 to n minus 1. So x belongs to the set 1 to n minus 1. Okay. So take all these elements, that is your Zn star, and what we will show is that the set of false witnesses is a strict subgroup of Zn star. So that is our line of attack. Show that the false witnesses forms a proper subgroup of Zn star. Okay. So any proper subgroup, its size must divide the size of the group, and therefore Lagrange, so that is Lagrange's theorem. So Lagrange's theorem says that would imply that size of the set of false witnesses so if we look at the set of all false witnesses, the set of, so that set, its size will be less than, let us say, n by 2, okay, because Zn size is at most n, okay, and the false witnesses, since it is a strict subgroup, its number must divide the group or the size of the entire group. So it is going to be less than n by 2. Okay. So now how do we show that this collection of false witnesses is a proper subgroup? First we will show that it is a subgroup. So we can write this as two sub goals. 1.1 would be, so let me call this as f. So f will be a subgroup of Zn star, and then we will show that f is not equal to Zn star. So that would mean that it is a strict subgroup. So we will exhibit one element which belongs to Zn star, but is not belonging to f. Okay, so let us just look at, we'll just write the numbers that we check: a to the r, a to the 2r, a to the 4r, and so on up to a to the 2 to the s r. These are the elements that we are considering for any a. Okay. Now let us look at these numbers r, 2r, 4r, and so on. Okay. We will define what is called as a bad power. Okay. So r, 2r, 4r, etc. are the powers. These are the numbers to which we are raising a. So bad power, the definition of a bad power is, so we will say that S is called a bad power if there exists an x such that x to the s is equal to minus 1 mod n. Okay. So look at x to the power s, all these computations carried out in mod n. If it is equal to minus 1, then we call this as a bad power. Okay. So in this entire thing, we will essentially be working in the group Zn star. Okay. Zn star consists of all those elements which are between 1 and n and are relatively prime to n. If you multiply two elements from there, you will in fact get another element in the same collection, and you can do cancellation there. So that is indeed a group. Okay. So we will call a particular element S from these R, 2R, 4R, etc. as a bad power if you can find an element in Zn star such that x raised to s is minus 1 mod n. Okay. And here is a crucial fact: I will define GS to be this set of all numbers such that, so let us say all y such that y to the s is equal to plus or minus 1 mod n. Okay. So, for any bad power I define this particular collection of sets, they do form a group. Okay. So, we have to say that GS is a group under multiplication mod n. In other words, GS is a subgroup of Zn star. Okay. How do we verify this? You take any two element in GS. So, if you multiply them, y1 y2 is a product. Does this belong to Gn? So, GS clearly is a subset of Zn star, okay, because we are looking at only those elements y belonging to Zn star, which is this property. So, GS certainly is a subset, the elements which form the collection GS is certainly a subset of Zn star. Now, you take two arbitrary elements y1 and y2, if you take their product, okay, that is y1 y2, y1 y2 to the power s is going to be equal to y1 to the power s times y2 to the power s. This is equal to plus minus 1 and this is also equal to plus minus 1. Their product is also going to be plus minus, I mean it is either plus 1 or minus 1 mod n. So, that would mean that GS is closed under multiplication, under the group operation. Therefore, GS has to be a any subset which is closed under the operation, that has to be a subgroup. So, GS is clearly a subgroup of Zn star. Now, the particular subgroup which contains all the false witnesses, we will define that in a moment. So, choose say S star to be the largest bad power. So, look at all the bad powers, amongst them find the largest, that is what we define as S star. Is there even one bad power? Only then it makes sense to talk about largest. Okay. So, we are looking at these numbers R, 2R, 4R, etc. Amongst them is there at least one bad power. Clearly, R being an odd number is surely a bad power, because minus 1 raised to R is going to be minus 1. Okay. So, R clearly is a bad power, minus 1 here means P minus 1. So, therefore, the number R which is an odd number surely is going to be a bad power. 2R, 4R, these are all even numbers, they may or may not be bad powers, but we want to look at the largest bad power, let that be S star. Now, corresponding to this largest power, look at GS star, that is going to be a group, because we had earlier shown that GS is going to be a group for all possible values of S. Okay. Therefore, GS star would automatically be a group. So, GS star is a subgroup of Zn star and all the false witnesses belong to GS star. Okay. Why is this so? So, let us say A is a false witness. Okay. So, clearly we need to show that A raised to, so if we want to show that A belongs to this particular group, so we need to prove that A belongs to GS star, okay, that is if A is a false witness. Okay. What we know is A raised to R a raised to 2r, a raised to let us say 2 to the I times r, etc. And if you look at this all the way up to a raised to 2 to the s r, this has to be 1. Okay. Now, there is a last point at which, so look at the last point at which there was a 1. Okay. So, let us say that was a raised to 2 to the I plus 1 times r, this is 1. And at this point, so let us look at these 2 raised to I. Okay. So, 2 raised to I and s star, which is going to be larger, 2 raised to I times r and s star, which of these elements has to be bigger. So, since s star is a bad power, okay, we know that so it is the largest bad power. We know that there exists a x such that x raised to s is equal to minus 1. This would also imply that for all x, x raised to s plus 1 should be greater than or equal to, this should be, this will not be equal to minus 1. So, we look at the last point at which there was a transition to 1. Since A is a false witness, at this point the only number that could have occurred is minus 1. Okay, because if it was 1, then of course the last point, we assume that the last point at which a 1 appears is 2 raised to I plus 1. So, this is not a 1. If it is not a minus 1, that means we have found a non-trivial square root of unity. Since both is not happening, we can conclude that a raised to 2 raised to I times r is equal to minus 1. So, therefore, we can conclude that 2 raised to I times r is a bad power. Okay. And since S star is the largest bad power, we can conclude that 2 raised to I times r is less than or equal to S star. Okay. Therefore, if you take a raised to S star, that is going to be equal to, sorry, yeah. So, if you take a raised to S star, then that is going to be equal to a raised to 2 raised to I times r plus let us say t, t is greater than or equal to 0, and a raised to 2 raised to I, okay, and S star is, let us assume it is equal to 2 raised to alpha times r. Okay. So, this entire thing a raised to S star would be a raised to 2 raised to alpha r, which is equal to a raised to 2 raised to I r the whole raised to alpha minus I. Okay. So, whatever. So, this is coming after 2 raised to I. So, this is going to be equal to plus or minus 1. Okay. So, this would imply that A must belong to G S star. Once again, since a raised to 2 raised, I mean a raised to 2 power I times r was the last point at which it transitioned into 1, in which the sequence transitioned into 1, we can conclude that a raised to 2 raised to I times r is equal to minus 1. This would also imply that since S star comes after this, a raised to S, I mean, so S is a number of the form 2 raised to I times r, which comes after I. So, a raised to s star must be equal to plus or minus 1. Okay. So, we have now concluded that every false witness must in fact belong to Zn star. Okay. Now, what is remaining is to show that we can construct an element which does not belong to Zn star. That means, sorry, we can construct an element which belongs to Zn star, but does not belong to Gs star. Okay. So, remaining part, we will write it as a claim Gs star is a proper subgroup of Zn star. Okay. So, since S star is a bad power, we can conclude that since S star is a bad power, there is an x which belongs to Zn star such that x raised to S star is equal to minus 1. Okay. So, this is minus 1 mod n. Now, what we can additionally assume here is we are looking at a composite number, and that composite number has the feature that it is not a to the power b, it is not a perfect power. In particular, we can assume that it is not a prime power. So, we can write n as equal to product of two composite numbers n1 n2 such that n1 and n2 does not have any common factors. Okay. So, n can be written in this particular way. So, in order to construct the element, so our proof will go like this. We will construct an element which belongs to Zn star but does not belong to Gs star. Okay. So, that element will have the following properties. We will call that element y. So, y will be equal to x mod n1, and this will be equal to 1 mod n2. Okay. So, x is this particular element which shows that S star is a bad power. That means, x raised to S star is minus 1 modulo n. Okay. So, take that x, and our y is going to be x mod y is going to satisfy two equations. Y should be x mod n1 and it should be 1 mod n2. Is it always possible to find solution to these kind of equations? Okay. So, it is possible, that is what is known as Chinese remainder theorem. Okay. So, let us see an example of Chinese remainder theorem. So, let us take n is equal to 7 into 5, that is 35. Okay. And somebody asks me to find an alpha, says that alpha is equal to 1 mod 7 and it is equal to, let us say, 4 mod 5, okay, and this alpha must belong to say 1 to n minus 1, okay, or 0 to n minus 1. So, can we find an alpha which satisfies these conditions? Our condition here is essentially similar. We have n1 and n2 which are relatively prime, they do not have any common factor between them, and we are asked to find a y between 0 to n minus 1, 0 here will not work. So, we can because the equation insists that it is 1 mod n2, so starting from, so your y is some number belonging to Zn star which satisfies these conditions. So, in this case why is it possible to always find one such? Okay. The proof essentially that one can find such is based on the following observation. Take all the 35 elements from let us say 0 to 34. Okay. So, any element let us say x is being mapped to the following pair. Okay. So, this is, let me call it as x1, it is mapped to x1 x2 where x1 is equal to x mod 7 and x2 is x mod 5. Okay. So, every number is basically mapped to a pair of numbers, the first element in the pair being x mod 7 and the second element being x mod 5. Clearly x1 can take 7 different values and x2 can take 5 different values. So, the total number of values that they can together take is less than 35. So, x1 x2 the total choices is going to be less than or equal to 35. Okay. So, for every number we are doing this for all x ranging from 0 to 34, we convert them into pair. So, for example, if we had taken 1 that maps to 1 1, 2 maps to 2 2, 10 maps to 3 and 0 and 11 would have mapped to 4 comma 1 and so on. Okay. So, we are looking at the total numbers of the kind x comma y or x1 comma x2 that can appear. Maybe we can say that it is no more than 35, but do all the 35 numbers appear? So, we can say that all the 35 pairs of the form x y where x is less than x1 is less than 0 and 6, x2 is less than x2 lies between 0 and 4, there are 35 such choices. If we say that none of the pairs repeat, then we can say that everything appears once and exactly once. So, how do we say that none of the pairs repeat? So, for example, if something here had repeated, let us say x1 x2 is so x maps to x1 x2 and y also maps to x1 x2. Okay. What does this mean? If you look at x minus y, okay, let us assume x is larger than y, x minus y is divisible by 7, right, because x leaves remainder x1, y also leaves remainder x1 when divided by 7. So, x minus y should not leave any remainder, okay, because x is equal to x1 plus k times 7, k1 times 7 and y is equal to x1 plus k2 times 7. So, if you take the difference, x minus y is equal to k1 minus k2 times 7. Okay. So, we can argue that x minus y is divisible by 7, and we can also argue in an exact same way that x minus y is divisible by 5. Okay. The only number between 0 and 34 which is divisible by 7 and 5 is 0, that means x minus y is equal to 0. Okay. So, we can argue that x is equal to y. In other words, it is impossible that two distinct numbers x and y maps to the same pair. Therefore, every particular pair will be present. This means that alpha equals 1 mod 7 and alpha equals 4 mod 5 has a solution in the range 0 to 34. Clearly, it cannot be 0 because 0 would not have given 1 as the remainder mod 7. Okay. This proof can be converted into to a formal proof where you take two numbers n1 and n2, such that n1 and n2 multiply and give n, and they do not have any common factor between them. Okay. So, we can show that there is one number between 1 and n minus 1 which leaves remainder x when divided by n1 and remainder 1 when divided by n2. So, what have we achieved? We have constructed one particular element, but how do we say that this element does not belong to GS? Okay. We also have, so we have to show the two things. Y belongs to Zn star, and the second thing is y does not belong to GS star. These are the two statements that we want to prove. In order to show that y belongs to Zn star, we should show that GCD yn should be equal to 1. Okay. So, the defining property of y was y is equal to x mod n1 and this is equal to 1 mod n2. So, we have this equation that y minus x is equal to k times n1. Okay. So, GCD x n1 is equal to GCD y n1. Okay. Because from this equation, if x and n1 had a common factor, okay, any common factor of x and n1 would in fact be a common factor of y. Okay. So, GCD x n1 would be equal to GCD y n1. Also, GCD x n is equal to 1. So, x does not have any common factor with n, because x did belong to Zn star. In particular, x cannot have any common factor with n1. This would imply, since GCD xn is equal to 1, this would imply that GCD x n1 is equal to 1. That would imply that GCD y n1 will be equal to 1. Okay. And from this equation, we can conclude that GCD y n2 is also equal to 1. So, we have argued that GCD y n1 equals 1, GCD y n2 is equal to 1. That means, y does not have any common factor with n1 or n2. So, therefore, GCD y n is equal to 1. So, we have already managed to show that y belongs to Zn star. Y does not belong to GS star is what we need to show. Okay. Now, this is because, so if y belong to GS star, then the defining property of GS star is y raised to s is equal to plus 1 mod n or y raised to s is equal to minus 1 mod n. Okay. But our y has this property that it is equal to x mod n1. So, if you take y raised to s, that will be x raised to s mod n1 and this has to be equal to minus 1, because x raised to s is equal to minus 1 mod n. So, x raised to s is equal to minus 1 plus k times n1 n2. So, this would imply that x raised to s is equal to minus 1 mod n1. Okay. So, this is minus 1 mod n1. Okay. So, clearly this is the only possibility. So, y raised to s is minus 1 mod n1 and y raised to s is equal to 1 mod n2. So, the defining equation for y was y is equal to x mod n1 and this is equal to 1 mod n2. Therefore, y raised to s is equal to 1 mod minus 1 mod n1 and it is equal to plus 1 mod n2. Okay. So, let us say if y belong to GS star and if this condition is true, y raised to s is equal to 1 mod n1, then we can conclude that y raised to s is equal to 1 mod n1 as well, but that will directly contradict with this. So, this is not possible. If y belongs to GS and y raised to s is equal to minus 1 mod n, then we can say that y raised to s is equal to minus 1 mod n2 and that will contradict with this condition. Okay. So, in either case we get a contradiction. Okay. So, once again, suppose y belongs to GS star, there are two cases. So, case 1, y raised to s is equal to 1 mod n, okay, and the case 2 would be y raised to s will be minus 1 mod n. But our y had the following properties, y is equal to x mod n1 and it is equal to 1 mod n2. If y raised to s was 1 mod n1, this would imply that y raised to s is equal to 1 mod n1 as well. Okay. But since y is equal to x mod n1, we have y raised to s is equal to x raised to s mod n1, but x raised to s was minus 1. So, this is minus 1 mod n1, that contradicts with this. If y raised to s is minus 1 mod n, in that case y raised to s is also, this would imply that this is equal to minus 1 mod n2. If y raised to s is minus 1 mod n2, that directly contradicts with y equals 1 mod n2, because if we raise both sides to power s, we will get y raised to s is equal to 1 mod n2. So, in either case we get a contradiction. So, that would mean that y does not belongs to GS star. So, that essentially means that the set of all false witnesses, they form a subgroup, and since the subgroup is at most half the size of Zn star, Zn star's maximum size is n minus 1, therefore, you cannot have more than 50% of the elements as false witnesses. Therefore, our algorithm has more than 50% chance of success in each run. So, repeat the algorithm as many times as you want the, depending on the probability of success that you are happy with.